All right, so first let's talk about the singularity formation result. So the key to this result is the moving plane method, which some of you might be familiar with for constant mean curvature surfaces, but one that is adapted for geometric flows. So this formation result will apply specifically to weak solutions of the inverse mean curvature flow, ones which were introduced by Huisken and Ilmanen to solve the Riemannian-Penrose inequality. And to introduce their notion of weak solution, let's first say that you have a bounded open domain in Rn+1, and you'd like to solve the following exterior Dirichlet problem. So you'd like a scalar function u that satisfies the following PDE, div of nobly u over norm nobly u equals norm nobly u on the region exterior to E naught, and that u restricted to the boundary of E naught is equal to 0. We'll call this star. So if you have a u solving star with non-vanishing gradient, what you can show is that its level sets, so the set of all points where u equals t in this domain, its level sets will form a classical solution to the inverse mean curvature flow, where the initial data is taken to be the boundary of E naught. The problem is that solutions to this exterior Dirichlet problem do not always exist, because of course you don't always have global classical solutions to inverse mean curvature. So as a way of getting around this, Huisken and Ilmanen developed a notion of variational solutions to star. Now, I won't present their precise variational formulation of star because it's quite complicated, but maybe I'll just mention the key properties. So a variational solution to the problem that I just presented is a locally Lipschitz function. And even where it's differentiable, it might have points where its gradient is equal to 0. So in other words, you consider u that are allowed to flatten out over regions, okay? Now, you can consider the weak flow surfaces of u to be the boundary of all points where u is less than t, so almost like the level sets of u, but not quite, because the level sets aren't necessarily hypersurfaces if this is true. So you consider these almost level sets of a variational solution u, and basically wherever the function u flattens out, this corresponds to some sort of jumping phenomenon in the weak flow surface n tilde of t. I didn't quite draw this picture right, but if you think of n naught as being the boundary of these two balls, and you think about the classical solution evolved from this initial data and the weak solution evolved from this initial data, there will be some region in Rn+1 where u is constant over a set of positive measure. And what happens when you reach that region with the classical solution is n tilde of t will jump past this constant u portion of Rn+1 and then continue flowing. So I drew this picture a little bit wrong because technically the jump doesn't happen right at the time t, it happens after the time t, but this is the picture. The n tilde of t are allowed to keep flowing forever wherever you have this flattening out for the variational solution, because variational solutions to the previous problem will always exist over Rn+1 minus E naught. Okay, so this is a notion of weak solution to inverse mean curvature flow. And let me describe the method that I use to analyze these weak solutions. So the method of moving planes that I used in my paper was very similar to one that was proposed by Bennett Chow and Robert Gulliver in a 2001 paper. So let ET be the set of all points where u is smaller than t for a variational solution. And you can prove a reflection property that these ETs must respect. So first, fix a plane in Rn+1 called P lambda nu. This plane divides Rn+1 into a lower half plane and an upper half plane, depending on the orientation of P, or of nu. Part of E naught might lie in the lower half plane while another part lies in the upper half. So we'll say that initial data E naught is admissible if the part of E naught lying in the lower half plane gets reflected into the part which lies in the upper half plane. And what you can show is that if this is true for E naught, it's true for every single ET. So if you take the same plane that you had before, divide up into lower half plane and upper half plane, and reflect across it, the part in the lower half plane of ET will get reflected into the part in the upper half plane. So you have some sort of symmetry for the weak flow surfaces from this. And I should also mention that, like, I guess the plane here really isn't the thing that is moving. So if you'd like to call this the method of moving planes, just think of the motion of being relative. It's more of just like a nice little buzz term, I guess, calling it the method of moving planes. But this is the reflection property that you have. And using this reflection property, you can show that the weak flow surfaces n tilde of t will be star-shaped by the time that it's fully escaped the largest ball containing n naught. So in other words, take n naught, surround it with some ball. You know that once n tilde of t is completely outside of this ball, it must be star-shaped, which is useful because you know a lot of things about star-shaped inverse mean curvature flow. And you can, using an avoidance principle for weak solutions, actually estimate how long it will take for this to happen. So the time that I got that it took for this to happen was n times the log of lambda max times diameter of n naught. And let me just remind you again that lambda max is the largest principal curvature of n naught. So you can estimate how long it will take the weak solution to become star-shaped in terms of n naught, which is the boundary of E naught. Okay, well, this is nice. It tells us something interesting about weak solutions, but this entire presentation is supposed to be about classical solutions. So what can this tell you about a classical solution? Well, in order to answer this question, we need to ask, when does a classical solution define a weak solution? I was saying before that if you have a U over some domain in Rn plus 1 that solves this PDE, its level sets will always satisfy inverse mean curvature flow. But maybe let's flip this question around a little bit. If you have a classical solution to inverse mean curvature flow, when can you somehow use it to define a U that solves this PDE? Now, when I say define a U, think about the region that all of the flow surfaces NT cover in Rn plus 1. So the union of all of the NTs, and call this U, this region big U. So we would like a scalar function little u from big U into R defined the following way. We'd like its level sets to each correspond to a flow surface NT, so that U of x is equal to t if you have a point x in NT for a given t. So defining this U will only make sense if the flow surfaces at different times are disjoint from one another. So if you have NT1 intersecting NT2 for T1 not equal to T2, this U wouldn't be well defined, because how do I say if it's equal to T1 or T2 if I take a point that lies in the intersection? So what I was able to show with just elementary flow properties is that the function U will be well defined as long as each NT is an embedded surface. So if you have, if you start with a solution U to this problem, its level sets will automatically be embedded. But what I showed is that if each flow surface to a classical solution is embedded, you can always define a solution to this problem, conversely. Okay, and why is that useful? So basically, what this tells you is that the only way that The weak solution doesn't correspond with the classical solution is either if the NT go extinct or if they fail to remain embedded. Because if you have a classical solution that exists for all time and is embedded, it will define a U over Rn plus 1 minus E naught that solves this problem. So then by uniqueness, it's the only variational solution over the set. So the source of jumps in n tilde of t will always be either extinction in finite time or self-intersection. Now, what you can do using the geometry of minimizing holes is you can basically predict how long it will take for a jump in, or sorry, how long it will take for an intersection or finite time extinction to happen in terms of the time that n tilde of t jumps. So if n tilde of t, say, jumps at the time 1/2 t star, that will tell you that the eminent singularity or self-intersection will happen by the time t star. And this is the key to proving the main theorem on formation. So you can show that if any jumps in n tilde of t happen, that like using the star-shaped thing that I mentioned before, that any jumps in n tilde of t must happen within this prescribed time interval. And if jumps in n tilde of t happen within this prescribed time interval, then singularities and self-intersections and nt happen within this prescribed time interval. Okay, so either you have nt corresponding with n tilde of t for all times, and that was part A in the alternative that I showed you before, or either a singularity or a self-intersection happens. And using this result from the moving plane method, you can show that if singularities or self-intersections happen at all, they must do so within the time t star, which again is 2n times the log of largest initial principal curvature times initial diameter. So it's a number that's somewhat similar to the number that you see for mean curvature flow, singularity formation. And that's the key to proving the formation result.